Okay, recording started. Shared my screen. My screen is visible to you now?
Yes, sir.
Okay. So what is random forest? We'll see the definition first. Okay. So random forest regressor is a supervised machine learning algorithm. This is one of the supervised machine learning algorithm used for regression tasks. So for regression purpose, we use random forest regressor. It is a part of the ensemble learning family. Okay, we'll see ensemble learning family also, what it is, which combines multiple models, in this case decision tree, to produce more robust and accurate predictions. So assembling means like by the assemble or assembling what you get, means by literal meaning what you get.
Like so we can say like two merge or others like means to together like to keep it together.
Same. So this assembling allow multiple models to combine and do the performance. Okay, so this is a we will use this assemble from sklearn, is a popular in scikit-learn and popular Python library for machine learning. Okay, majorly we use sklearn. This module provides implementation of assemble learning algorithm, so which we saw here, assemble learning family, that is the assemble learning algorithm, which are method that combines the prediction of multiple individual models. Okay, so you get it, guess it right, like more than one model it can provide to produce a more accurate and robust prediction. So whatever the result our model is trying to predict, if with the single one it is not giving us the accurate one, so we can use this assemble family model. Okay,
Yes, sir.
the same one. Assemble learning is a machine learning technique where multiple models called base learners, okay, this is also called as base learners, are combined to solve a problem and improve overall performance. Instead of relying on a single model, assemble methods aggregate the prediction of multiple models to produce a more robust and accurate prediction. Fine.
Yes, sir.
So this assembly family model we use to make a proper or accurate production. So till here definition and assembling part is clear.
Yes.
See the program now. So again here we are using this same model, NumPy, Matplotlib and Pandas. We imported the library here. Then this part is our data set, importing our data set. On left side if you see we have a position salary CSV. So these are the values. If you see there are position level salary 3 columns. So here from pandas we are using dot read under CSV file because this is the CSV file, so we read it. Again dataset dot iloc, whole rows whole column, and here first column values first to second. So this is the dependent variable we saw in our last examples, right? Sorry,
Independent, sir. Independent.
independent variable, right? And this y is a dependent variable, so whole rows second column we are predicting it. So if you see from this, position level will be our x axis, means independent variable, and salary we are predicting as a y axis. Then splitting and feature scaling we are not doing. Then directly we are applying a random forest regressor. So from sklearn we are using assemble and importing random forest regressor. Then we are creating an instance of this regressor class, random forest regressor, and estimator. This is one of the parameters, so it will take approx 10 samples, and random state 0 means it will seed those randomly generated value. Fine. This line of code is clear.
Yes, sir. Yes, sir.
Okay, then we will fit this x and y. So regressor.fit function, we provided the x and y value. Then we are predicting a new result. Regressor.predict. Inside it, we are providing a value 6.5. It will hold the result into y underscore predict variable. Once it is done, we will try to see the result. So visualizing the random forest result, higher resolution. So here we are taking numpy dot arrange function we saw already earlier, similar like range, where it will give us the value between start and end. So here from x it will take the minimum, then max, and it will take a step, like it will be the, suppose we given one step, so one it will skip two, then three, like that. We saw that step example, right,
Yes.
in our Python series. And then from this x grid on we are doing a reshape. So whatever the length of x grid will be, so it will give us the length, and this is the one. So based on this range it will reshape our x grid. Then we are using a scatter method from matplotlib, means plot scatter, provided the value of x and y, it will make a color. Then we will plot x grid, this x grid, regressor dot predict, it will predict the x grid and it will make in a color blue. Then these four are title, x label, y label, and so. Let me run it. So this is our result. This is a one kind of random forest regressor. Okay, fine. So if you see in blue color, this is the part which is predicting. Okay, and this is the our actual data x and y. So if you see, almost it predicted.
It is in the tree structure now.
Correct, correct. So this example is clear. It is for
Yeah.
forest.
Like sir, just sir, like means why we are not just like what we can say like using that training means that, but firstly train and test model.
Hmm.
Yeah, means I just want to ask like why we are not using here like in this code. We are not training or testing, no, like
If you want, you can do it now. No
okay,
issue.
okay.
You can train it. So assembling, already it is combined multiple one, and uh, like it is not a single algorithm na. In this class only it is defined as a multiple ways. So here if you see, based on our data, it is like as a tree like structure. So if you use the same data for a decision tree algorithm, so the result we get in the same way, right?
Okay, sir.
We saw that example for decision tree also, right? Or let
Hmm.
me show you that example as well, so you will be able to relate it. So I'm replacing this code with the decision tree one. Okay, we have the same
Yes.
data set. Let me run. See, it is also give us the same like structure. Okay,
Yes, sir. Hmm.
so this is a regressor only. Here also we see we have disabled it. Let me enable it, and Okay, I have enabled these two and let me run. Okay, here is a how this code
So it
become
is at starts like after that feature scaling.
fine. Okay, see, same result, right? No much difference.
Okay, same result, yeah. Huh.
Hmm. So when you deploy, then you have to train the model, test it, then you can deploy it. This is just for our understanding purpose, so something we are commenting it. Fine.
Yes, sir.
So this is for decision tree. Let me run this for again random forest. See. So you are getting a little difference between these two graphs or not? Hello, am I audible this?
Hello.
Yeah,
Yes, hello.
yeah. So what I'm trying to say, like in this graph, in random forest as well as in decision tree one, so you are getting any difference between these two graphs?
Yes, so like there like means just a slight difference, not much.
What difference you identified?
So that I think that 1.0, I think incidentally there is also like the curve is also reaching there. I think.
Okay, let me run both the code. So this is for
Okay,
random forest. Okay,
I
I will,
think that.
so maybe you will be able to guess it. So this is for random forest. I will give for decision tree as well. I have run both the code in the same. Let's see. Okay, so this is for random forest, first one. My screen is visible.
Yes, sir. Random forest is visible. Like.
This is a random forest and this is for decision tree.
Yes, sir.
What difference you are getting now?
So could we scroll little bit like.
Or let me small it so it can fit into both. Fine.
Okay, sir. Yes, sir. Yes, fine.
What difference you are getting here?
Mm, like I said, sir, that first one that curve at a 1.0 means 1.0 salary range.
See, where you are saying 1.0. This one.
So in graph like
Okay, due to value also it can differ, but in both the places value is same. Okay, in graph where you are saying.
so around 1.0 salary
Hmm,
in a random forest.
hmm,
And if we compare it with the decision tree,
hmm.
then it will just say like means there is just the change in the curve.
Right.
Okay.
Okay. So this is a little difference. So random forest and decision tree both algorithm is clear to you now.
Yes, sir.
Let's move to the next one. So we saw simple linear regression, polynomial regression, support vector regression,
Decision
decision
tree, yeah.
regression, random forest. Okay.
Random forest.
Now we will see the how we can calculate the performance of model, means evaluating regression models performance. So this is my code where we are trying to uh, evaluate the performance of our model. So let me give a little explanation also where something we will encounter. Let me comment this. So result, in result we'll see this is MAE, just this is just a variable name which we are doing here, mean absolute error. So what MAE, MSE and RMSE? So lower values indicate the model makes fewer error. Okay, when we will get a lower values, which indicates we are going to get a uh, more accuracy level result. Then R squared, a value of R squared is 0.92, means the model explains 92% of the variance in the target variable. We'll see in our example. Let me start from here. So first we are using a numpy. Okay.
Import, yeah.
Okay, then from sklearn we are importing make regression from data sets. Then train and test we already saw. Okay, random forest regressor we already saw. Okay, and from sklearn metrics we are importing mean absolute error, mean squared error, and R2 score. So these are three ways by which we are trying to evaluate our model performance. Suppose if you do the average, suppose 2 plus 2, it will come into 4. Okay, 2 into 2, 2 multiplied 2, it will also come to 4, right? And
Mm.
2 plus 2, you said 2 multiplied 2, it will also come 4. And 1 plus 1 plus 1, 4 time if you do, it will also come to 4, right?
Yes, sir.
Okay, so based on the result with three approaches we are trying here similarly. This is a one way, this is another way, this is the third way. And based on this, we'll try to predict the accuracy of our model. Fine.
Yes, sir.
Okay, now we are generating a regression data set. So uh, we do not have referring any uh, actual data. We are just generating randomly from this regressions only. So make regressions. N samples means we are taking a 500 samples. N features means 5 column. Noise means it will take a kind of like we saw the example of degree. So it will be some up and down kind of data which make the model more realistic data to accept. And random state 0 means it will see the randomly generated value. Fine.
Yes, sir.
Then splitting the data, train test, train train test, XY, test size 20% of that means 500, 20%, how much it could be? 100 data, it will be utilized for testing purpose. Random state 42. Okay, no issue. Then this digit does not make much difference now, it will seed only. You can make it 0, you can make it 42. So we will
Okay.
change
Mm.
while getting a result, we will change both and check it. Okay, then initialize and train the random forest model. So first we will initializing this class random forest regressor and estimator. If you see, it is 100 sample, random state 0. Then we are fitting in this data into model, X train, Y train, make prediction on test set. So here we are doing on a test set model.predict x test, and here we are calculating the result, mean absolute error, y test, y predict. So this will predict y test, y predict using this mean square error and numpy dot square root msc. This result we are storing into that. Then we are calculating r square, y test, y predict, and here result of MAE, MSE, RMSE, two decimal point, and R square. So let me run this. So this is our result. So what we said here, lower values indicate the model makes fewer errors. Okay. So this is the lower value through mean absolute error, mean square error. It is giving more than through this root mean square error method it's giving this value, and from r square it is giving 0.92. So this is the more suited one based on our accuracy. If we go with this, it is giving us that our model is predicting more error related work. Okay, so a value of r2 square 0.92 means model explains 92% of the variance in the target variable. Best practice: use multiple metrics to evaluate a model, as each provides a unique perspective. Compare metrics across different models to select the best performing one. So based on that, which model give you the better accuracy, you can select that one. Use cross validation for more robust assessment of model performance. Okay, so we will not rely only on one accuracy parameter. We'll try to evaluate more than one accuracy parameter. Fine.
Yes, sir.
Just note it down, or let me copy it and put here. So we'll change that, or we will run it again and we'll observe do we are getting the same result or not. See, same result we got. Let me run second time
Yes,
for
sir.
same result we got, right?
Yes, sir.
Now we will make a change in this random one. Okay, let make it 0 and run it. Do we are getting any difference?
Yes, sir.
Where?
MS, MSE, MSE.
Right. So there is slight change in data because we have made it, and here also r2 square
Yes,
0.92.
yeah.
Now let's make it 2 here. So it will not make much difference, but fine, we can run it. So now see, it is giving a little difference,
Yes, sir.
32, 194, and here it 87%,
Yes, sir.
like that.
Like say it means the more the value is accurate, no? Like the lesser the value, like
See,
it means there is an error.
this thing is nothing. It is just freezing your randomly generated value. The value of this parameter is that one only. Let me
Okay.
show you. Okay. Random state none. Okay. Generates a random generation regression problem. Where is for see here it is giving like noise 1, random state 42. Okay. So this is the value. It we whatever the value, suppose here there is a 500 sample you given, 5 columns, noise 0.2%, 0.2, and random state 2. So whatever the data randomly it is selecting, it will freeze it. So this parameter will not make much difference. Okay.
Okay.
Because when you randomly generating, so there is a chance, suppose we have a 10 rows and start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So first time you generated, so 5% of that, suppose 5 column started from 1 to 5. So sum of that could be 1, 2, 3, 6, 6 plus 4, 10, 10 plus 5, 15. Okay. But next time when you generated, it started from second, not the first one. So like
Okay.
that, your value can differ, right?
Yes.
2, 3, 4, 5, 6. Okay. Suppose you are taking how many values? 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 values we have. We are taking 80%. So suppose it taking this much in randomly. Second time it is started from here. Third
Okay.
time it could be started from here. So value will always differ because it is randomly picking and seeding those value, freezing those value, right?
Okay, sir.
Fine.
Yes, sir.
Usually you will find more like 0 and 42 majorly I saw with these examples. Okay.
Yes, sir.
So this evaluation of a model Example is clear?
Yes, sir.
Then we'll see the regularization method. You heard about the overfitting and underfitting concept?
No, sir.
This is a program. Let me explain a little bit from this. Or let me explain this program first, then we'll see those. So here again, this is for regularization. It is also known as normalization, which we do on that feature scaling part. You know,
Yeah, yes.
feature scaling we do, right? If we have to make our data in a standard
Memory.
form
Yeah.
or normalization form. So
Yes, sir.
this is the one. So sklearn from sklearn data set, we are making importing make regression. This is a linear model. From this, we are using these three: ridge, lasso, elastic net, and this is model selection for training and testing purpose. Metrics we are using mean square error. Okay. Now generating a data set through this regression. So make regression, sample is 100 and feature 5, column noise 0.5, random 42. See here also we use 42. On this line we are splitting the data: X train, X test, Y train, Y test. Train test split provided the value of X and Y. Test size is 20%, random state 42. Now there are three ways. Okay, if you see, I am using ridge regression, lasso regression, elastic net. Okay, and we are calculating the result and plotting it. So ridge regression alpha, we are giving zero point 0.1 ridge, then ridge dot fit, providing a training set of X and Y. This ridge is predicting X test, so based on our testing data. Similarly, lasso regression, this is also known as L2, L1, okay, and this is known as combination of L1 and L2,
Combination. Yeah.
okay. Here alpha we are giving 0.1, train, test, sorry, training, both the training, and here we are predicting it, lasso dot predict. Now elastic net, same thing. If you see here, we just given one more parameter, ratio 0.5, X train, Y train, elastic dot predict, X test, and now calculating mean square error. So this is a ridge SME Y test ridge method, ridge one, which we are predicting here. For lasso SME MSE Y test lasso, there are three ways. Okay, then elastic MSE mean square error Y test elastic, and here we will print those values. Then for plotting purpose, we are using matplotlib. Coefficients of ridge, lasso and elastic net. Figure we are taking between 10 to 6. It should take plot ridge coefficient O dash ridge. Label should be ridge coefficient. Same thing, lasso coefficient,
So
lasso.
actually, all these are like means all these are the built-in methods. No, that lasso dot coefficient, elasticity dot coefficient, and underscore.
Hmm.
Oh, yeah.
What I didn't get what you were saying.
Okay, so I just want to ask, like, means all like this, like that apply, yeah, that first three, like,
Hmm.
yeah. So all these are built-in methods, no, like to just
Yeah,
train.
built in.
Okay.
And here we are just giving a name, na? Label you can modify.
Yeah,
Okay.
yeah, yes, yeah.
Okay. Then plot that Excel line 0, color black, line style should be dash dash, line width should be 0.7, and these five are: one is title, X label, Y label, legend, like it will give us a kind of highlighted part, we can say. Okay, we'll see in a result. And so let me run this. See, so this region, these are uh, legends. Okay, so whatever the legend we have given now, so there are three labels. Okay, so label will be treated as legend, so that is a legend. If you see on my mouse cursor part, legend
Yes, sir.
coefficient, lasso coefficient, and there are three lines. So if you see how this now, this O which we given, it is like, if you see, this is a dot, so this is a O form, then there is a dash. Okay, instead of dash, let me give some different one and try. Okay, I given this. Okay, it is not taking. See, you got that format, we given double dash, so second line
Okay.
here it is
Yeah.
taking as a double dash, right?
Double dash line. Yeah.
Okay, got it. So this left, top left side is my label. Means this legend part is clear now, how this legend is generated.
Yes, sir.
Okay,
Just for highlighting, like. Okay.
yeah, so I commented that part, so see that output is not showing on our graph, right?
Yes, sir.
Hello. Yeah,
Yes, sir.
so if I uncomment it, so it will show. Then these are just title, X label, Y label. So coefficient value, featured index, so this is the featured index X, this is Y. These five are straightforward, and this is the coefficient. So one, we saw this. If you want to change, instead of O, let me give some other symbol, what it could be. Let me try. No, it is not taking at the rate. Let me, do we are able to get a p value? If you see the second value
The
where we have given dots,
yeah.
given us some different value, right?
Yes, sir. Yes.
So this is a symbol which is compatible with this function. You can apply those. Fine.
Yes, sir.
Now this program is clear.
Yes, sir.
So this is one of the regularization or normalization way. And there is some statement here. Interpreting result, like for ridge regression. Okay. This is a ridge regression result. Then minimizes overfitting by shrinking coefficients, but all features remain in the model. That is for lasso. And drive some coefficient to 0, effectively performing feature selection. It is for, it is lasso is close to 0 now. Then elastic combines region lasso, useful when there are many correlated features. Okay, so this is for that. That is the result. So you heard about this term overfitting and underfitting. There is two terms.
No, sir.
Okay, so in a model, this overfitting and underfitting is two concepts. So our model should not predict the over biased value or under biased value also. Okay, so I have that. This program is clear to you, right? Hello, am
I'm
I audible?
audible. Yes, sir.
Yeah, I'm
Yes, yes, yes.
asking like this program is clear to
Yes, sir.
you.
Yes.
Okay,
Yes,
we'll
sir.
move to the next one. So in this we saw the one random forest one and how we can evaluate the regression or model performance, and this one regularization method. In that we'll see two more ways for like overfitting and underfitting, so I am sharing those concepts. So I have shared my document. Is it visible?
Yes, sir. Yes.
Okay. So what is regularization? So regularization is a technique used in machine learning to prevent overfitting. Okay. So by adding a penalty term to the loss function, this penalty discourages the model from becoming too complex. Okay. Such as having very large coefficients in regression or overly complex decision boundaries in other algorithms. So there are three ways which we saw, like as lasso. There are three types of regularization technique. So add the absolute value of the coefficient to the loss function, encourages sparsity in the model by driving some coefficients to exactly zero. So lasso, we saw the example where it was giving us the result close to 0.35, right?
Yes.
Then this is the formula, but in calculation term it is already come under the functions. Then ridge L2 regularization, it is known as add the squared value of the coefficients to the loss function, then shrinks coefficients but does not make them exactly zero. So in last ridge we didn't got an example close to zero, so it will not exactly make to zero. Useful when all features are important but should have small weights. Then third one, elastic net, combination of L2 and L1 regularization, balances between sparsity L1 and smoothness L2. So this is a regularization technique which we saw in the program. Now why we use regularization? To prevent overfitting by penalizing the large weights in the model, to improve generalization of the model or unseen data, to handle multi-collinearity in regression model. So there are three reasons we use regularization. Now this is for result which we saw, minimizes overfitting by shrinking coefficients, but all features remain in the model. Then lasso drives some coefficients to zero, close to zero, we are going to get a result, effectively performing feature selections. Then combines ridge and lasso, useful when there are many correlated features. Till here fine?
Yes, sir.
Okay, so in which scenario we can use these two? So good for feature selection. Okay, some coefficient shrinks to zero. Then ridge, all coefficient shrinks but remain non-zero. Works well for multi-collinearity and balance between L1 and L2, useful for high dimensional data set with correlated features. So regularization majorly, which we saw earlier also, feature scaling we do if it is required. Now come to overfitting. So for overfitting purpose, we use the regularization method. What is overfitting? It is a common problem in machine learning and statistical modeling where a model learns not only the underlying pattern in the training set but also the noise or random function in the data. As a result, what is the drawback of overfitting? The model performs very well on the training data but poorly on unseen or new data, that is test data. So that is the cause of overfitting. You got it now?
Yes, sir.
So when we train the data, it will give us the fine result. Okay. But when we train the model and we tried the same model to predict on the test data, it will not give us the as expected result
Correct.
which
Okay,
we saw.
correct value. Yes.
Okay,
Mm.
fine. So opposite of that will be the underfitting. Okay.
Mm.
So cause of overfitting, excessive model complexity, using models with too many parameters. Example, high degree polynomial regression or DNN, deep neural network, for relatively small data set. Then this complex model can memorize the training data rather than learning generalizable pattern. Okay. So what happens? They memorize. Suppose you have given some training data, it keep referring those data. Even if you are giving some new data, it is not trying to learn from new data. So that is one of the scenario in overfitting. Then insufficient data. A small training data set can make it difficult for model to generalize, and model might capture noise as per the pattern. Okay, so for that you also need a good amount of data to train your model. Then too few data processing steps, lack of feature selection, data scaling, or feature engineering can make the model too sensitive to irrelevant features. Means we do not have much data where we can do the feature scaling and all. So there is a chance our result in training data it will give us good, but on testing it can vary. Okay.
Okay,
Then
sir.
sign of overfitting. What is the overfitting? Identification, high accuracy or training data set. So every time you are getting a good result, the model shows excellent performance. Example, very low error or high accuracy on the training set. So this is one of the way by which we can identify it is overfitting. Poor performance on test data. Model performs significantly drops on the test data or any new data it has not seen before. Okay, if you are giving some new data which is not looks like in a, which is not being trained in a training data, so it will not try to predict something different. It even in those scenarios it will try to give us the good result in train. Large variance in prediction. The model predictions are highly variable and sensitive to small changes in input data. So these are the signs by which we can see. So this we already cover, explained the code. Now overfitting, how we can avoid it. Use simple models, choose model with fewer parameters, or use simpler algorithms that does not have too much capacity to overfit, like linear regression or decision tree with shallow depth. Increase data size, then regularization we can use, cross validation we can use, pruning. In decision tree algorithm, pruning can be used to remove branches that are not contributing significantly to the model. Okay. Then early stopping. In neural network, early stopping can prevent overfitting by halting training once the model performance on the validations set starts to degrade. Okay. So in that there will be nodes. Then visualizing overfitting, how we can visualize it. When a model overfits, it typically performs very well on training data. So this is a repeated thing. But so it will
Yes,
give
sir.
us a good result in training, but on testing, it's give us a
Test data, it will,
expected result.
poor
Okay.
data. Hmm.
Underfitting, then here is the concept plot shows overfitting, then underfitting, the model is too simple and does not capture the data's underlying pattern. Good fit, the model generalizes well, capturing the overall trend in the data. Then overfitting, the model becomes too complex and follows where every fluctuation in the training data which doesn't generalize to unseen data. So how we can avoid? We can use simple models, more data, regularization, cross-validation, and other techniques. By these ways we can avoid the overfitting. Now there is one more concept, underfitting. Underfitting occurs when a model is too simple to capture the underlying patterns in the data. Okay, very simple model. It happens when the model does not have enough complexity or flexibility to learn from the training data. Okay, therefore performance poorly on both the training set and new unseen data. So it is giving training and testing also. It is giving us the poor performance. Cause of underfitting: too simple models, insufficient training. If the model trains for too few epochs or iterations, it might not have had enough time to learn the relationship in the data. Okay. Too strong regularization, like regularization method like L1 or L2, can prevent overfitting, but if it applied too heavily, it can also prevent the model from capturing useful parameters and leading to underfitting. Okay. Poor feature selection, so standardized use too few or irrelevant features in the model can lead to underfitting, since the model may not have enough information to learn meaningful relationships. Sign of underfitting: high training errors. Okay, so it is giving error in training as well as in testing. The model performs poorly even on training data, including that it has not captured the patterns in the data. Low model complexity: the model is too simple for complexity of the data, such as using a linear model for non-linear data. Poor performance on test data as well, since the model is too simplistic, it will not generalize well to new unseen data either. So in overfitting, it is giving us a good result in training, but not in testing. But in underfitting, it is giving poor result on both the scenarios,
Both
like
the
in
side, yeah.
training as well as in testing. We have saw this how to avoid use more complex models like polynomial decision neural network, increase model training, train the model for more epochs iterations, so run again and again. Reduce regularization, we can use reduced regularization to follow the model. So you asked me why we have not done the feature scaling, right? So based on the result you will do the feature scaling as well. If it is required then you will do, otherwise you will not do. And more features, use more relevant features or engineer additional features to give the model more information to learn from. Choose right algorithm, so select an algorithm that matches the underlying data characteristic. For instance, a non-linear model like decision tree or SVM might be more appropriate for non-linear data set. So if you use vice versa, like for non-linear data you are using linear regression, or for linear regression kind of data you are using non-linear, so it can give us such error or result. Okay. Visualizing underfitting. In contrast to overfitting, where the model fits the data too closely, underfitting involves a model that is too simple to capture the underlying data pattern. Okay. Underfitting, good fit, overfitting. The straight line that does not follow the data, that's curve. Okay. That is underfitting. A curve that captures the overall trend of the data, and a curve that follows every small fluctuation, noise in the data. So what happens in underfitting happens when a model is too simple or not trained sufficiently, resulting in poor performance on both training and testing data.
Test data, yeah.
Okay, so in overfitting, it is giving only in training, but in testing not as
Mm,
expected result.
What I expected, yeah.
But here in both the scenarios, testing and training, it is giving a bad result. To avoid underfitting, use model complex, means complex model, train the model accurately, reduce excessive regularization, and ensure that you have enough relevant features. Fine.
Yes,
So we saw underfitting, overfitting definitions, regularization techniques, random forest, and evaluation of model. Fine. Till here, any doubt, any
yes,
question?
no, sir. No, sir.
Okay. So have you started any of the program for machine learning?
So actually, I've started in like it's in my friend's laptop, like,
Mm.
but I will start it in my laptop as well. Like I've so firstly, I'll what we can say, like I've just been completing, or else we can say like writing all the theory concepts first, and then going towards the coding.
Okay, try. So we have a 2 days off,
Yes,
so
yeah,
we will
that's
try
what.
on that. From Monday, I will start giving you the assignment as well.
Sure, sir,
So
sure.
almost regression part we have covered. So we will drive to next part of the machine learning. So before that, I want you to be at least have hands-on on this regression algorithms. Okay,
Yes, sir. Yes. Sure.
so we'll stop here today. Thank
Sure.
you.
Thank
Bye.
you, sir. Have a good